Hi, in this video I will begin a new chapter which is called copula. Copula. I will explain what this is in a minute, but before that, suppose you have x comma y, which is a random vector, right? There are many situations where x and y will be dependent on each other. Okay. Now I'll give you a couple of examples. Example 1 is where x comma y equal to the oil price and the car price. Obviously these two variables are dependent because whenever the oil price goes up, the car price will also go up, right? And the example is where x comma y is equal to the oil price and food price. Again, these two variables are dependent on each other because once again, when oil price goes up, the food price will also go up, right? Now, a copula, this is the topic of this chapter. A copula can be used to model the dependence among two or more variables. In this chapter I shall focus only on two variables, but the copula can also be used to model the dependence among more than two variables, right? Now, I'm going to give a loose definition of a copula. This is not the formal. The formal definition will come in the next video, right? Now, this is just like a loose definition. For when you have two variables, a copula is a function, okay? It's a function which is denoted by the letter capital C and is defined from the unit square, 0, 1 times 0, 1 is the unit square, to the unit interval, right, with the following conditions, with capital C u comma 1 equal to u, which means that, all right, let me write this down before I talk, and capital C 1 comma v is equal to v. What these two means is that the marginal cumulative distribution functions of capital C are uniformly distributed on the interval from 0 to 1. That's what these two conditions tell you. That this tells you that the marginal distribution of the first variable is uniform 0, 1, and this tells you the marginal distribution of the second variable is uniform 0, 1. Now, before I go ahead, let me just highlight a few things. Now, this thing here is the unit square. I'm sure you know this. And this is the unit interval. So copula is a function from the unit square to the unit interval. Okay. All right. So what I've given you here is not the formal definition. It's like a simple loose definition. The formal definition of a copula will come later in the next video. Now suppose you have a random vector x comma y has the joint CDF. Okay, and marginal CDFs. This is the marginal CDF of x and the marginal CDF of y. Now I'm going to give two statements. Statement 1, statement 1 is the following, that for every joint CDF, all right, there is a corresponding copula. Right, and I'm going to prove this statement in a sec. So this is the proof. Okay. Now I'm going to start with the joint CDF of x and y. I'm sure you know that the joint CDF is defined as the probability that capital X is less than or equal to little x, capital Y less than or equal to little y. Now I'm going to do the following. I'm going to, on both sides of this inequality, I'm going to take you see what I'm doing. Okay, and the same thing for this, but this time okay. Now in the next step, I don't know whether you know that whenever you have a random variable x and if you are taking the CDF of the random variable x, what you get is the uniform random variable. So what I'm saying is that the CDF of a random variable, right, is one of the properties which I will write down in a minute. The CDF of a random variable is simply a uniform random variable. And the name of that property, I will write it down in a sec. So this statement, that is the step from this to this, follows because of what is known as the probability integral transform. All right, this is something you ought to have learned in year 1 or year 2. But if you haven't learned it or if you don't remember, just try to remember this, that the CDF of a random variable is the uniform random variable, right? Okay. Okay, now I'm going to, because I said a minute ago that the copula has the marginal distributions equal to the uniform distribution. So we can write the above as C okay. That's because, as I said a minute ago, a copula is made up of two margins, and the marginals are uniformly distributed. So we can write this joint probability as C of this comma this. So hence we have proved that for every, just to go back, okay, for every joint CDF of X and Y, there is a corresponding copula C. And that's what we have to prove. Hope this is clear. Okay. All right, guys. Okay. Now, there's a second statement I'm going to prove in a sec, which is the following. This is statement 1. Statement 2. Statement 2 is the following. This statement is the reverse of the statement number 1. So this statement says for every copula C, there is a corresponding joint CD of X and Y. Okay, so let me prove this as follows. Okay. So for this proof, I will start with the copula function, which is capital C UV, right? And now remember, the copula is made up of two uniform random variables, so we can write this as the probability of a uniform variable 0, 1 is less than or equal to U times another uniform variable 0, 1 less than or equal to V. Okay. Now what I'm going to do is the following. I'm going to take on both sides of this, I'm going to do the following. Okay. And the same thing with this. Right. Now, in the next step, I'm going to use a different version of the probability integral transform, which says that you should take the fx inverse of a uniform random variable. What you get is the random variable x. So this becomes x. That's because of exactly the same result I used earlier, that is the probability integral transform. And similarly, this becomes y. Okay. So let me say that again. So this line here follows because of the probability integral transform. Right. Now what you have here is simply the joint CDF of x comma y at okay. So hence we have shown that for every copula, we have shown statement 2, that is for every copula C, there is a corresponding joint CDF of x and y. So the proof is complete. Okay, hope you follow this. Okay. So we have shown the statement number 2 and also statement number 1, right? All right, in the next slide, I'm going to talk about two of the simplest copulas, right? Number 1 is known as the independence copula. And is defined as follows. So the independence copula is simply U times V, which is the same as saying, right, because a copula, as I said before, is a joint distribution of two uniform random variables, you can write the left-hand side as this. Okay. Now I'm going to take, like I did in the previous slide, I'm going to take on both sides of this inequality and the similar thing for this one. Okay. Now, by the probability integral transformation, this guy here is simply x, right, less than equal to and this guy here is y. Okay. Okay, so this follows by this step here, once again follows by the probability integral transform. Okay. Okay. Now I'm gonna do the following. I'm gonna set this guy here and this guy here. So I'm going to set this equal to little x and this equal to little y. All right. So what I'm going to get. So in other words, what I'm doing is, let me write this. Setting x equal to this, which implies that little u is capital Fx of x. And also I'm setting y equal to this, which implies that little v. Okay. So setting this, the above statement can be written as follows. Okay, and this is what you have on the left hand side is the joint CDF of x and y. Right. Okay, and if you look at this equation here, all right, what you have here is the joint CDF of x and y equal to the product of the marginal CDFs. And you may recall from your previous years, year 1 or year 2, this is the usual definition of independence between x and y. Okay, so what we have shown is that this copula, let me go back to the beginning. What we have shown is that this copula here, which is the independent copula, corresponds to the variables x and y being independent. Right, so we are shown that this is equivalent to this, which is the usual definition of independence between two random variables x and y. Okay. Now the second of the two copulas, I said I'm going to talk about two simple copulas. Right. The second is as follows. So the second copula is known as the completely dependent copula. Right, and and it's defined as the following. Okay. Now this is equivalent to saying that the probability okay. Now in the next step I'm going to use the probability integral transformation as I did in the previous slide. Okay. Now in the next step I'm going to use the probability integral transformation. So this guy here once again becomes capital X. And this guy here once again becomes capital Y. So let me write this. So this follows because of the probability integral transformation or transform. Okay. Okay, now before I go to the next line, I'm going to set, as I did in the previous slide, I'm going to set x, little x equal to this, which implies that u is equal to, okay, and also I'm going to set little y equal to this, and which implies that v, okay, so under this transformation, this statement here can be written as follows: as the probability that x less than equal to little x, capital Y less than equal to little y, of the minimum of, okay, and this, the left hand side, can be written as the joint CDF of x comma y. Okay, and this, what you have here is precisely the definition for complete dependence of two random variables x and y. So this, I don't know whether you did this before in your previous years, but this is the usual definition of complete dependence. Complete dependence between two random variables x and y. Okay, so just to summarize what I have done here, I have started with this copula here, right, which is known as the completely dependent copula, and shown that this is equivalent to this, which is the usual definition that two random variables x and y are completely dependent, right? So this completes this video, and in the next video I shall give you the formal definition of a copula and also do some examples.